Hello again. Now that we've developed and learned how to use the chain rule, there are some other situations where we can learn to use it. One of those situations is what's called implicit differentiation. This type of differentiation allows us to take derivatives of not functions, but rather relations. So expressions that can't be written in an explicit form. So not in the form, y equals f of x, but more of a relation. We can apply this technique called implicit differentiation to calculate the derivative. So let's build this idea and learn how to use it. So here we're asked to find some derivatives. Alright, so for example, what's d by dx of x? The derivative with respect to x of x is 1. We learned that a few sections ago. But what's the derivative with respect to x of y? Well, we've said that the derivative with respect to x of y could be written as dy dx, or we could write that as y prime. But now what if instead of just y, what if we had y square? So here's where we can apply the chain rule. If we sort of assume that y is related to x, y is a function of x, then differentiating y square is like using the chain rule. The derivative with respect to x of y square would be 2y times, and then from the chain rule, d by dx of y. So then that's the same as writing 2y by dy dx, or 2y times y prime. It's not just 2y, because we're not differentiating with respect to y, we're differentiating with respect to x. We have to be very careful about the notation and understanding what the independent variable is that we're differentiating with respect to. So then what's d by dx of cosine y? Same idea. If we assume y is a function of x, then we can apply the chain rule. The derivative with respect to x of cosine y would be negative sine y times dy dx, or negative sine y times y prime. Similarly, why don't you find the other two? What's d by dx of e to the y, and what's d by dx of x times y? Now would be a good time to pause and try these on your own. d by dx of e to the y, applying the chain rule, that would be e to the y, since the derivative of an exponential is the exponential itself, times dy dx. Or again, we could write that as e to the y by y prime. Now d by dx of x times y, we have to be a little bit more careful here, because what I see is that this is actually a product. I have x times y, and x is a function of x, and if we assume that y is a function of x, then I have to apply a product rule. So I'd have the derivative with respect to x of x, which is 1. Then I'd leave the y alone, plus I leave the x alone, and then I find the derivative with respect to x of y, so dy dx. So then I could write this as y plus x times dy dx, or y plus xy prime. Okay, so this is just some basic concept of how we differentiate various functions with respect to x. And there's nothing really special about the y. I could have used a different variable if I wanted to. For example, what's d by dx of z to the 5th power? Well, then that would be 5z to the 4th, and then by the chain rule, dz dx. Alright, so now that we have some idea of how we find the derivative with respect to x of various variable expressions. Now let's actually talk about implicit differentiation and how it applies to relations. So here we're given the relation x cubed plus 4y squared is 17, and we're asked to find dy dx and to find the equation of a tangent line at the point on the curve, the point 1, 2. Now the issue is, if we have x cubed plus 4y squared equals 17, I could solve this equation for y and write it in an explicit form. I'd have to be careful though, because if we sort of think about the process, at some point I'd have to use a square root property, right? Because if I have a y squared equals something, then y would equal plus or minus square root. And then I'd have to decide what's the appropriate square root. I could do that in this case. However, I can also use a different technique called implicit differentiation. So let's start with the x cubed plus 4y squared is equal to 17. If we want to find dy dx, what I can do is differentiate both sides of the equation with respect to x. So let's find d by dx of both sides of the equation. All right, on the left-hand side, let's see, d by dx of x cubed, that's pretty straightforward. That's 3x squared. D by dx of 4y squared. Now here's where we have to be careful. The derivative with respect to x of 4y squared would be 4 times 2y times dy dx. D by dx of 17, 17 is a constant, 0. So I now have 3x squared plus 8y dy dx is 0. Now, if I want to find dy dx, I can solve for dy dx in this equation, and that'll give me an expression for dy dx. So 8y dy dx is equal to negative 3x squared, just subtracting 3x squared from both sides, and dividing through by 8y, dy dx is negative 3x squared over 8y, or you could bring the negative out front, right? That would be negative 3x squared over 8y. It's the same expression. So there's dy dx. Notice that this dy dx is not just in terms of x, it's also in terms of y. And so that's what's different. Remember, if we were finding the derivative of a function of x, the derivative was going to be in terms of x. Here we're finding the derivative, the dy dx, of a relation of x and y, and it turns out that that derivative is also in terms of x and y. So there's part 1. dy dx is negative 3x squared over 8y. Then we're told the curve passes through 1, 2. Find the equation of the tangent line at that point on the curve. All right, well, we need a slope and a point. Hey, we've got the point, right? We know the point on the curve is 1, 2. We need the slope. Well, the slope would be equal to dy dx evaluated at the point 1, 2. Right? The dy dx is in terms of both x and y, so the dy dx we're going to need to use both x and y. So then dy dx evaluated at 1, 2 would be negative 3 by 1 squared over 8 by 2, which is negative 3/16. So then the equation of the tangent line would be, we could write it in the point slope form, y minus 2 is negative 3/16 by x minus 1. And if we wanted to, we could take this to the slope-intercept form. Y equals negative 3/16 x plus 3/16 plus 2, and 2 is 32/16, so plus 35/16. Let's go ahead and check and see if I did this right. Now, graphing this relation x cubed plus 4y squared equals 17, our calculators are going to have a tough time with that, because our calculators, the TI-83, 84 calculators, they like the function form, y equals some function of x. But Desmos can handle this pretty quickly. So we have x cubed plus 4y squared equals 17. So here I'm on Desmos.com. Let's type in x cubed plus 4y squared equals 17. And we have this graph. And let's plot the point 1, 2. So there's the point 1, 2 on the curve. And let's see, let's graph the equation. The equation that I got was y equals negative 3/16 x plus 35/16. Let's go ahead and graph that as well. So let's see, let's graph y equals negative 3/16 x plus 35/16. And that certainly appears to be tangent to the point. And if I zoom in some, I'm just zooming in on 1, 2, it certainly does appear to be tangent at that point. So the method works, right? And this implicit differentiation concept certainly does work. So here's another example. Write the equation of the tangent line to square root x plus square root y equals 4 when y equals 1. Why don't you try this on your own? All right, so again we have a relation, and I could, again, solve this equation for y to get this in an explicit form. I'm going to go ahead and just apply implicit differentiation. So then d by dx of square root x plus square root y would then equal d by dx of 4. Alright, so d by dx of the square root of x, that would be, we've seen this a few times before, thinking of that as x to the 1/2 power, then the derivative would be 1/2 x to the negative 1/2. So I'll write that as 1 over 2 root x. Now, square root of y, the derivative of square root of y with respect to x would be 1 over 2 square root y times dy dx. And that would equal 0. Again, using a little bit of algebra here, I'd have 1 over 2 root y dy dx is equal to negative 1 over 2 root x. And then I'll multiply both sides by 2 root y. So then dy dx is negative 2 root y over 2 root x. And we can simplify that. Dy dx is negative root y over root x. So I now have the dy dx, but this one's a little different than the previous exercise. Here we don't have a point, a complete ordered pair. We have one of the coordinates. We have y equals 1. All right, so let's complete the ordered pair. If y equals 1, then square root of x plus square root of 1 equals 4. So then square root of x, the square root of 1 is 1. Subtracting 1 is 3. Square root of x is 3. And so then x is 9. So that means the point on the curve is 9, 1. So then the slope on the curve would be dy dx evaluated at 9, 1. And so that would be negative square root 1 over square root 9. That's negative 1/3. So then writing the equation, I'd have y minus 1 is negative 1/3 of x minus 9. And again, I could take this to the slope-intercept form. That would be y equals negative 1/3 x plus 3 plus 1 plus 4. Y equals negative 1/3 x plus 4. Why don't we go ahead and check this one out as well using Desmos. All right, so we have root x. Let's clear these out. And let me go back. All right, so I've got square root of x plus square root of y equals, it was 4, right? All right, so let's do that. Zoom out a little bit. We get this interesting shape. All right, and we ended up with what point? I forget the point now. It was the point was 9, 1. Let's plot the point 9, 1. Okay, so there's the point 9, 1 on the curve. And let's go ahead and graph y equals negative 1/3 x. Oh, let's put the x here. And plus 4. And again, that certainly does appear to be tangent to the curve at that point. All right, so now that we have this idea on how we can find that, let's look at a couple more examples of applying implicit differentiation. All right, so here we have a relation y to the 4th plus x squared y is equal to 6 minus x y squared, and we're asked to find the dy dx. So notice that in this equation, the y appears more than once, and so what happens with this is we're going to end up with multiple terms that have the dy dx. And so we'll have to do a little bit of algebraic work to then find the dy dx. All right, so like I've done before, let's apply the differential operator d by dx to both sides of the equation. Okay, and I'm not going to rewrite the whole thing, but I'm applying the differential with respect to x to both sides. All right, so then d by dx of y to the 4th, that would be 4y cubed dy dx. Plus, now x squared y, that is a product of functions. Let's apply the product rule. So that would be 2x times y plus x squared dy dx. And so I'm using parentheses there to show that those two terms are coming from the product rule. Right hand side, this equals the derivative with respect to x of 6 is 0. Minus, and then again xy squared, again I'll have to use a product rule here. So I'd have 1 times y squared plus x times 2y dy dx. So now notice that I have several terms that have the dy dx associated with them. So notice that all the dy dx's are all raised to the first power. So what I'm going to do is I'm going to get all the terms that have dy dx on one side of the equation, everything else on the other side of the equation, and then I can use some factoring to solve for dy dx. All right, so let's see. I'm going to bring everything with the dy dx to the left-hand side of the equation. 4y cubed dy dx plus x squared dy dx. Oops. Now, I had a minus. Be careful here, right? I have this minus that's distributing. And if I bring that to the left-hand side, it's going to become positive. So then I have a plus 2xy dy dx. So everything with the dy dx is now on the left-hand side. Everything else, let's bring to the right-hand side. So let's leave this term here, a negative y squared, and I have to bring this term to the right, minus a 2xy. So now notice that everything on the left-hand side has a factor, all the terms on the left have a factor of dy dx. So I could write the left-hand side as dy dx times 4y cubed plus x squared plus 2xy. The right hand is still negative y squared minus 2xy. So then just a little bit of division, dy dx is then equal to negative y squared minus 2xy divided by 4y cubed plus x squared plus 2xy. And so there's dy dx for that given relation. Why don't you pause and try the second exercise here on your own. Find dy dx if x squared times e to the y is equal to y. Alright, like I did in the previous exercise, I'll go ahead and apply the differential operator d by dx to both sides of the equation. Applying the product rule on the left-hand side, I'd have 2x times e to the y plus x squared times e to the y dy dx. The right-hand side, d by dx of y would be dy dx. Alright, and so again I see two terms that have dy dx. So I'll bring all those to one side. I'll bring them to the right in this situation. So then 2x times e to the y is then dy dx minus x squared e to the y dy dx. Notice now that the right-hand side could be written as dy dx times 1 minus x squared e to the y. And that's equal to 2x e to the y. So then again, applying a little bit of division, dy dx is then equal to 2x e to the y divided by 1 minus x squared e to the y. Alright, so we have to be a little bit more careful in these situations where we have multiple terms that end up with a dy dx. Once we calculate the derivatives correctly, then it's just algebraic manipulations to isolate the dy dx. So now suppose that x is a function of t, y is a function of t, and z is a function of t. Differentiate this relation with respect to t. Now would be a good time to pause. Try this one out on your own. Alright, so here we have to be careful. We're asked to differentiate with respect to t. So we're going to apply a differential operator, but not d by dx. Since we're differentiating with respect to t, we're going to apply d by dt to both sides of the equation. Now what that means is, well, we're not differentiating with respect to x. The derivative of 3x squared is not just 6x. It is 6x times dx dt. D by dt of 6 sine y. That would be 6 cosine y times dy dt. Minus the derivative of natural log z. That would be 1 over z dz dt. Now the derivative with respect to t of 7 is still 0 because it's still a constant function. 7 is still constant, so its derivative with respect to any variable is 0. Now this idea that I just showed, this differentiating with respect to t, this is going to be important in a later topic called related rates, where we're going to have a general formula. We're going to work with certain formulas that will have variables dependent on t, and like time, and we'll have to differentiate with respect to t. So we're going to see this idea again soon. Alright, I'm going to stop this video here. We're at about 25 minutes. And then I'll pick up in the second video with another technique that's related to this called logarithmic differentiation. I'll see you there.